Physics students, good afternoon. Mr. Fugger here. In our video today, we're going to be working through group problem 5A. There might be a little bit of confusion with some of the notation. If you were in my regular physics class, then we might have covered a slightly different problem in 5A. This specifically video is going to be over group problem 5A as it relates to the test tube ride, which we covered more directly in my STEM physics class. So if you have a little bit of difference in the notation, or if you're a little bit unsure as to which problem that we're going to work through, this is for group problem 5A as it relates to the test tube group problem and not the washing machine ride. As always, the problems that we're going to be working through, copies of them are available on Canvas, as well as a key to the problems that we're going to be working through. If you need that information, you're welcome to look on the Canvas page to get what you're looking for. So, group problem 5A. Here what we're going to be doing is using our understanding what we've been covering recently over circular motion as a way to double check if a certain ride is going to be safe as it relates to the g-force that passengers might be subjected to. So we'll be looking at some of our equations for g-force and for centripetal acceleration, as well as using some of the ideas of kinematics to find out things like velocities for some of the different parts on the ride. Now, as you'll see here, we don't have an actual copy of the problem. As I mentioned, the group problem is located on Canvas along with the key. Essentially what we're going to be looking at is a ride that I've called the test tube. Or we can say it's maybe a section of a roller coaster. The way the roller coaster is going to work, riders enter in on one side, they're dropped vertically downward, they come down to a circular portion and then back up. Right? As we've talked about with circular motion, oftentimes when an object, especially a person, is moving in a circle or part of a circle, they can be subject to very high amounts of acceleration. Even if even if the speed of an object doesn't necessarily change as it moves around a circle or a curve, oftentimes the acceleration can be very high because of the change in direction. And that's what we're going to be checking here. Is the proposed design for this roller coaster safe? And if not, how can we present a safe design? So one of the first things that we're asked to actually double check in the problem, after we've gone through looking at some of the background, a few things that you are given in the problem. The kind of length of the drop from where riders enter on until the beginning of the curved portion is about 30 meters. And we're also told that the riders begin from rest up here, where they enter onto the ride. We're told that the maximum amount of g-force that the riders are allowed to be subjected to is about 5 Gs. Realistically, people maybe could withstand slightly more than that, but given that this is a ride for an average person, we probably don't want to be putting them subjecting them to anything that's unsafe. And so what we're looking for here really is we're trying to figure out, is the design that we propose safe or unsafe? Now, given this information, one of the first things that we're asked to do is to take the g-force and convert that into a workable acceleration in standard units. So if we know passengers can only be subjected to 5 Gs, we can actually use our equation for g-force to figure out the actual value for the maximum acceleration they could experience. This would really go in part A of the group problem, if you're following along with the sheet. So g-force on an object is really not a force as we typically understand regular forces, pushes and pulls on or between objects. G-force is really a ratio of accelerations. And so here, if we're told that our maximum g-force limitation is 5 Gs, what that effectively means is that we don't want passengers to experience 5 times acceleration due to gravity, and that's a value that we know here for the Earth. So if our maximum g-force is 5 Gs, then the acceleration we experience cannot be more than 5 times acceleration due to gravity. So A is the acceleration we're looking for. Specifically as we move around this curved portion, that is going to be what we call centripetal acceleration. But g-force doesn't necessarily only apply to things that move in circles. Objects can be subjected to g-force, even if they're moving in a straight line. So we would then, in order to solve for our maximum acceleration for the riders, we would multiply our value for gravitational acceleration, and multiply that value to the numerator on both sides of my equation. So 9.81 over 9.81, those values would cancel out. And the maximum allowable acceleration is going to be 5 multiplied by 9.81, which should give us about 49.05 meters per second squared. And that value, again, is 5 times acceleration due to gravity for the Earth. That's what we mean with the limitation of 5 G's for the passengers. Now, one of the key components of what the problem is trying to get us to look for is, what is the allowable radius for this ride given our maximum allowable acceleration and the height of our drop at the beginning of the ride. So really the next part of the problem is going to ask us, now that we know this acceleration, where do we go? And one of the important equations that we've talked through as we have been learning about circular motion is that for an object moving in a circle, its centripetal acceleration can be expressed by the velocity squared of the object divided by the radius of the circle the object moves in, or the part of the circle our object is moving in. Now, at this point in time in the problem, we don't know the velocity and we don't know the radius, but we do know the acceleration. The problem statement tells us that the radius is something we want to try and find, which means that maybe we need to get to the velocity first and then get to our radius. So if we look back at the problem, one thing that we're told is that our riders are dropping a distance of 30 meters vertically. They're starting from rest, and we want to know what is the velocity at this point down here when our ride begins to move into the curved or banked portion. So we can maybe say that this is a velocity at some other point in time, not necessarily final velocity like the ending of the ride, but just after we've traveled the 30 meters. And if we can find that velocity, the problem tells us that the ride is set up in such a way that our speed does not change along the curved portion. The velocity, by definition, would change because velocity is not just how fast an object moves. Remember, velocity is a vector. It's the speed and direction of an object. So we do have a change in velocity here because we have a change in direction, but not necessarily a change in speed. So we do know how far we're falling. We're starting from rest. We can assume that the track is mostly frictionless, and that there's, again, we're going to ignore the effects of air resistance here as well, which means we can assume only the force of gravity is causing our object to accelerate. So really in part C, we're going to attempt to solve for a velocity, and we'll do that by using our kinematic equations. Here, the displacement of our object is 30 meters, but it's 30 meters downward vertically, so we'll refer to this as a negative 30 meters. We are starting from rest, 0 meters per second. We want to figure out how fast we're moving after we've fallen this certain displacement. So V1 is something we don't know. Acceleration for the direction we're in, the y direction, we will assume is acceleration just caused by gravity. We're ignoring the effects of air resistance and any friction on the track. And we don't know anything about time. We're not told anything about time in the problem, and time is something that we really have to have a kinematic equation to solve for unless we record it physically. So since V1 is what we want to know, that means time is the variable we don't know and that we can ignore. And using our kinematic equations, that means we're going to use equation number 5 as we've labeled it. And equation number 5 looks like this. V1 squared is equal to V0 squared plus 2a delta y. We know that our initial velocity is 0, so 0 squared, I'm just going to go ahead and write that value is going to be 0. And we can then move forward and plug in the variables we know to their proper place in the equation. So V1 squared is equal to 2, and again I'm dropping out the 0 simply because it's no longer a part of our equation. Acceleration in the y direction, negative 9.81 meters per second squared, our value for the Earth, and our delta y, 30 meters downward vertically, so negative 30. So V1 squared, I can take a moment, multiply 2 times negative 9.81 times negative 30. If you're watching, I would suggest you do this on your own. And we get about 588.6. Hopefully if you were doing this on your own, you would recognize that number is pretty high if we're dealing with a roller coaster car. That's not going to be something that's very realistic. That would be over 1,000 miles an hour. And that also is a good reason why we should not be finished here. So take a square root, because we want V1 by itself, not V1 squared. We don't want the velocity squared, we just want the velocity. So we square root 588.6, and we get about 24.3 meters per second. Now, technically, when we take a square root, there are 2 answers that we should get, a positive and a negative value. Here, if we wanted to be really technical, since our object is moving vertically downward on the ride, actually the velocity in the y direction here would be negative 24.3. We're really not as concerned with that value because we're going to square that value later on in our equation. But if we were going to present that as an answer, we would need to make sure that the direction follows along with the problem. Okay? So now that we have our velocity, we can come back to the equation we identified in part B, plug in to find our radius. So I'm going to use this because we know our acceleration because of our limitation on g-force. We know the velocity because of our kinematic equation. And now we can finish this out and solve for the radius. So here we go. This would be, I believe, part D of the problem. We've got our centripetal acceleration, velocity squared over the radius. Before I plug in any numbers, I'm going to rearrange the equation. I like to do that so that I can get the variable we're looking for by itself. So if I want to get the radius term alone, I'd have to multiply radius up to the numerator. Our radius would then cancel out. On the right side of our equation, we'd have something like radius times centripetal acceleration equals v squared. I would then divide by the centripetal acceleration on both sides of my equation. And I would be left with an equation for our radius that looks like this. Radius is now by itself, and that is equal to the velocity squared divided by the centripetal acceleration. If you feel more comfortable putting the numbers into the equation first and then rearranging, that works too. This is simply my preference. So now that we know our velocity, and here again, we could plug in a positive or a negative 24.3. Either way, that value will become positive when it gets squared, and then we divide by our centripetal acceleration, 49.05 meters per second squared. Plug this in, 24.3 squared. And I would suggest you do this as well as you follow along. Divided by 49.05, and we should get, depending on how you've rounded, a pretty clean value of 12 meters. Which again seems reasonable. It's about 36 feet-ish roughly. And so we're dealing with, again, with a roller coaster here. So there should be a sizable amount of radius to the loop. So that does seem to pretty much give us an answer to our question. We need about a 12-meter radius if we wanted our ride to be safe, given the height of our drop and the limitation on g-force. Now there is an extension for the group problem. This is part E, if you're following along. And in part E, you're actually asked to double check a coworker or another person's proposed design. Same roller coaster, but the difference in their design is the presented value for the radius is slightly less. It is 8 meters. And the presented value for the height of the drop from where the riders begin until where they enter into the curve portion is higher, it's about 40 meters. Now, as you can maybe guess, if we start the riders from a higher height, they're probably going to be moving faster when they enter the curved portion. And remember, centripetal acceleration is velocity squared divided by the radius. So if our velocity goes up, even if our radius stayed the same, if our velocity goes up, that means our centripetal acceleration is going to go up. Those values are directly related in this equation. But not only is our height of the drop bigger, but the radius goes down. And radius in our equation, as it relates to centripetal acceleration, is indirectly related to the centripetal acceleration. So that means if the radius goes down, the centripetal acceleration is also going to go up. So it seems just by thinking about this conceptually and looking at the equation, this is probably going to be an unsafe design. But as we see out in the physical world, it's not enough just to say something is unsafe. We have to be able to support why we think that's unsafe. So this design does give us a radius, so we already know that portion of our equation. Here, we really just need to find the velocity, very similar to what we did a moment ago. Now, we can assume that we're starting from rest, so our initial velocity is 0 meters per second. We can assume we're on the Earth, we're accelerating just because of the force of gravity on our object. So we're really going to use the same kinematic equation that we used just a moment ago. That was what we have called equation number 5. V1 squared is equal to V0 squared plus 2a delta y. Typically we go through and list out our variables in this process, but really our variables are almost identical here. The only thing that's changing is the height of our drop, okay, as it relates to this portion of the roller coaster. So here our initial velocity is 0, so I can go ahead and really cancel that part of my equation out. And I have V1 squared is equal to 2 multiplied by my acceleration, which we are assuming is just caused by gravity, negative 9.81 meters per second squared, and delta y here is negative 40. We're now dropping from a higher height. So we'll multiply through 2 times 9.81 multiplied by 40. We get about 784.8. But remember, that is our velocity squared. So to find just the velocity, which technically, if we're not really looking for what the velocity is, I could just plug that number in here, right? Because this is velocity squared. So I could do that, but it's probably good practice for us to just solve for what the velocity is, just in case we need it later on. We might not here, but if we were solving this in a real world situation, we would probably want to know that value. So here, V1, square root of 784.8. We get approximately 28.01. And just to make sure that we're not overlooking things, square roots always give us 2 answers, a positive and a negative. Technically, the right answer here would be negative because we're moving down. Well, that depends a little bit on how we define our coordinate system. Traditionally, downward in the y direction is the negative direction, so we can usually make that assumption. So now that we have our value, 28.01, we know the radius, we can solve for the centripetal acceleration, and that will then allow us to find our g-force. So now we've got a sub c is equal to our velocity. We could use positive or negative here. 28.01 meters per second, quantity squared, divided by our radius, which is 8 meters. We'll go ahead and plug these values in. Divided by 8, we get a centripetal acceleration of 98.1 meters per second squared. And then to finish out, our g-force is going to be our acceleration over acceleration due to gravity. So what we found, 98.1 meters per second squared over 9.81 meters per second squared. It's like a pretty clean ratio there of 10. Just to double check. Yep. Our g-force would be right about 10 g's, which on the surface we should be able to identify as probably an unsafe value for an average person. Obviously, it depends a little bit on the time in which they're exposed to this g-force. The chart that you're provided with in the problem tells us this would likely lead to some dizziness and loss of consciousness, which we probably wouldn't want to shoot for on the roller coaster design. So, in order to maybe make this design safer, we could increase the radius, drop or lower the drop height. That would maybe lead to some safer conditions for the riders. So here, hopefully we feel a little bit better looking at this version of group problem 5A, taking some of these ideas of circular motion and g-force and doing a little bit of analysis on a real world mechanical device. So if you have any questions, as always, you're welcome to ask. Hey, hopefully this video was helpful for you, and best of luck as you are solving.